we can draw this table here. Examine the symmetry between E and B. It turns out the electric field, just like any vector field, it's got, in principle, longitudinal part and transverse part, right? Again, the longitudinal part is provided by electric charge. Okay, that's Coulomb's law. And the transverse part is provided by what? A variable magnetic field. And that is the Faraday's law of induction. So basically, there are two ways to generate the electric field. If you want to generate a longitudinal field, you must have a charge, electric charge. If you want to generate a transverse type electric field, you must have a changing magnetic field. Okay, now conversely, let's take a look at the magnetic field. This equation tells us that there is no longitudinal magnetic field. And that's understandable because if you look at the symmetry between E and B, okay, electric charges cause longitudinal electric field. So if there were a magnetic monopole, we would have then probably would have discovered that the magnetic monopole would be the source of a longitudinal magnetic field. Okay, so the fact that this is 0 simply tells us there is no magnetic monopole. At least we haven't found one yet. So I'm going to put one here, rho m, m standing for magnetism. This is like a density of magnetic monopole. I'm going to put it in a bracket to indicate that does not exist or we haven't found it. But if we did, you would see the symmetry between E and B here. Okay, now continue. There is no longitudinal magnetic field, but there is a transverse magnetic field. That's described by Ampere's law, and Ampere says, okay, the way to create a transverse magnetic field is by using an electric current. So moving electric charges can cause magnetic field. That, of course, is the famous Ampere's law. IE standing for electric current, E standing for electric. Now, look at the symmetry between the transverse E field and transverse B field, and you can see clearly that you don't have the symmetry between these two cases. Okay, now, if a moving electric charge can cause a transverse B field, transverse magnetic field, then by symmetry, you would say that a moving magnetic monopole can cause a transverse electric field. So I can actually put IM here, magnetic current, that is moving magnetic monopole. Now, again, I'll put it in parentheses, in the bracket because we have never found it. But if we did, at least you can see there is a symmetry. But something here is conspicuously missing. See that? What's that? You see, a changing magnetic field can cause a transverse electric field. So, if you want to maintain symmetry, what do you think is missing here? Yeah, a changing electric field, right? A changing electric field, can it cause a transverse magnetic field? Okay? If we have this term, then indeed E and B will be totally symmetrical, right? You know, electric charge produce electric field, magnetic monopole produce magnetic field, and then so on and so forth. Partial B, partial D creates a electric field, partial E, partial D creates a magnetic field, and so on. Okay, but we have not examined this possibility yet. Something seems to be missing, and that's what's missing. So if you look at the symmetry, then you conclude that we should take a closer look at what happens when the electric field changes. You know, when the magnetic field changes, from Faraday's law we know we have an induced electric field, right? What if the electric field changes? Do we get an induced magnetic field? It's like the symmetrical part, the symmetrical counterpart of Faraday's law. Okay, so let's see. Let's create a scenario where there is a changing electric field. Okay, changing electric field, or in the integral form we say changing electric flux. And let's see what happens as a result. Okay, now you can examine this situation from the most general case, but that requires too much math for physics 1C. So what we're going to do is we are going to study a special case, just like we used, parallel plate capacitor and solenoids to calculate electric and magnetic energy density, right? What we're going to do here is we're going to examine a special case only. And using that special case, we can derive a very general result. Okay, so here is this special case. Suppose I got a very long and straight wire. Okay, it's a long and a straight wire carrying the current I. But there's something new on this wire. Okay, this wire is punctured by a pair of parallel plates, each capable of storing charges. So it's punctured by parallel plate capacitor, that is. And for simplicity, let's say each plate is circular. Okay, so it's like a circular disc, and it's centered at the running current. Okay, and we can make these two plates very close to each other. At one moment, we find that a current is running this way, so this, that takes positive charge, deposits positive charge on this plate, so the lower plate is positive charged, and the upper plate is negative charged. All right, now here's what I want to do. I want to apply Ampere's law to this case because I want to calculate the magnetic field. Okay, now imagine this. All right, suppose I look at a point that is quite far away, okay, from this capacitor. And this capacitor can be made very, very small, very, very small. And the gap between them is very, very small. And therefore, you can imagine that if the rest of the wire still carries the same current, the current only ceases to exist between here and there, an extremely narrow gap. So you lost only a very, very small segment of the infinite long current. Alright? Okay, every current segment produces its own magnetic field. This little guy is missing, but if you look at a point very far away from it, do you think the magnetic field at that point would really be affected a great deal by a little bit of missing current here? You don't think so, right? It doesn't make any sense. So you expect the magnetic field to be the same, as if this gap did not exist. Okay, because you have the current everywhere else except you're missing a tiny, tiny part, so it's not going to change the magnetic field far away from it. Now, how do you calculate the magnetic field? You say, oh, I know how to do that. Let me draw a, Amperian loop, right? Let me draw an Amperian loop. You can actually draw it into the circle and then whatever. And then you can calculate the magnetic, you can calculate this loop integral, contour C, and you have B dot ds over the contour C equals what? Mu naught I, right? Mu naught I. Okay? Now, on the other hand, we know this loop integral can always be rewritten by Stokes' theorem into a surface integral. Surface integral over surface area A. Okay, and here is gradient cross B dot dA. I can always do that, right? Now this area A does not have to be flat, as long as this area is bordered by this loop C. I can draw an area like this. I can draw an area like this, for example. It's like a dome, okay? So really think of this as a hat, okay? As a hat, with this as the rim, okay? With the contour as the rim, and then this hat, the bulged part of this hat is the area A. All right, it's got a hole here, but you integrate over this part only. Okay, and I can even look at what I do here. I can even stretch this hat so that it passes through the gap in between these two plates and come back. So you can think of this as a chef's hat, okay, very tall chef's hat, but it's also had the same rim, right? So this big red surface is also bordered by the same contour C. So therefore, it should also work. Now what is I, by the way? I is the current that penetrates through the area. Like if the area is like this, of course the area is punctured by the current, right? And if the area is like that, of course, it's punctured by the current here. But what about this chef's hat? Huh? This chef's hat, as you see, it cleverly bypassed the current because it goes through the space in between. Does any real current penetrate the surface of the chef's hat? No. So what do you think that side equals to? 0, right? But if that side equals 0, I is equal to 0, then doesn't that mean gradient cross B is equal to 0? Right? Doesn't that mean there is no flux? The magnetic field is 0? And it doesn't make any sense because if you look at this, okay, you look at this surface area, you say, yeah, it's equal to mu naught I. And then you just change the area A, and then all of a sudden you get 0. The other side becomes 0. That is not possible because either way, whether you use the red one or the silver one, either way, they're both equal to the same contour integral with the same magnetic field, right? So how can this surface integral be different from that surface integral? It doesn't seem to make any sense, does it? So we have a dilemma here. If we insist on using this formula, which is Ampere's law, by the way, we found that we can use it, no problem, if this is our surface. But we will have a problem if I use that particular area to apply Stokes' theory. Okay, so how does one solve this problem? Well, you realize that this is a special area A. Indeed, there is no current going through it. Okay, no current actually penetrates through the shell's head. But instead, okay, in lieu of the actual current, what does it have instead? Well, you see, there is an electric field penetrating through it over a certain area, and therefore there's an electric flux going through a part of that shell's head. And that electric flux, by the way, is changing. Can you see that? It must be changing over time. How do I know that? Because there is a current running through, going this way, which means the charge on either plate is changing. Okay, it's actually increasing. The current goes this way. And when the charge is increasing, that means the electric field is also increasing. Right? So there is an increasing electric flux, or in general, a variable electric flux. You know, variable magnetic field, or variable magnetic flux can cause electric field. That is Faraday's law. So, doesn't that give us a hint? Here we have a variable electric field. Just like a variable magnetic field can cause electric field, a variable electric field should also cause a magnetic field. In other words, it should be just as good as a current in creating a magnetic field. This dome has a current going through it, and that one has no current, but it's got something equally as good. And what is that? A changing electric flux. Okay, so you see, whether we use this surface or that surface, I should get the exact same in and out. I should get mu naught I, right? So what I'm going to do is I'm going to take a look at the electric flux. I'm going to write something that has to do with the changing electric flux, and that is equal to the current, to the real current I, and that is how I maintain, the correctness of this integral, even though I use that surface. Okay, so let's see how we can do that. This is a circular disk. Okay, and if the gap between is very thin, which I assume, then I can think of the size of each disk as pretty much infinity when it comes to calculating the electric field in between them. Okay, so I know how to calculate the electric field, and it is E equals to V divided by the distance between the two plates, which we call d, V over d, and V is Q over C by definition of the capacitance, and Q, because this is a parallel plate capacitor. I don't know what Q is. Okay, you remember what Q is? Epsilon naught A over D, remember? Okay, so when divided, okay, it's divided by C, it's epsilon naught A over D. So you see D and D cancels out. Okay, so what do you have left? It is equal to Q over epsilon naught A. Okay? And therefore, you move that A over, you get E times A, which is equal to Q over epsilon. But what is E times A anyway? The electric field over the region times the cross-section area of the region. Isn't that the electric flux going through the region? Okay, between, in between the two plates, electric flux, because the electric flux is uniform. Okay, so this tells us electric flux equals Q over epsilon naught. Now, the current, on the other hand, is not equal to Q. It is equal to dQ over dt, right? So to get the current, so what I'm going to do is I'm going to take the time derivative of both sides. Okay, I'm going to move that epsilon over, so I got epsilon naught d phi e dt equals dq dt. And that equals the current. Isn't that true, that I equals dq dt? So you see, over here I have a real current, which takes care of the right hand side. Over there, I don't have a real current, but instead I have something that's equal to the real current, which is epsilon naught d phi e dt. This quantity is equal to the current. Okay, so to make this formula valid, regardless of whether you choose this surface or that surface, let me add another term. Okay, let me add another term. Instead of mu naught I, I'm going to add mu naught epsilon naught d phi e dt. Why do I do that? Because if you take the mu naught out, you see it's I plus epsilon naught d phi e dt. Over this surface, I have only I. Over that surface, I only have epsilon naught d phi e dt. Okay, d phi dt. But they're equal to each other. You see that? So whether you use the red surface or that silver surface, you always get the same loop integral b dot ds. Okay, so therefore, this expression here is not a real current, but it's equal to the real current in terms of producing a magnetic field. So we give it a name. We call it the displacement current. Okay, so displacement current, ID, defined as epsilon naught d dt of E dot dA. Okay, the surface integral over the electric field. This is again called displacement current. And with the displacement current, I can write this. Okay, I can write the Ampere's law with this additional term, and I can write this as mu naught I plus ID. Okay, so here you have an I, you don't have an ID. Over there you have no I, but you have an ID, which is equally good. I and ID are equal to each other, you see here. So this is this new term that we're talking about. This new term was first discovered by none else than James Clerk Maxwell. And we attribute this to him, and therefore the original Ampere's law has a new term. It is now called Ampere-Maxwell's law. Okay, this gives us further evidence of the symmetry between the electric field and the magnetic field. So now I must go back and modify. I have one new term, mu naught I plus mu naught epsilon naught ddt E dot dA. Okay, that is the displacement current term. And I also have to rewrite here. What do I have to rewrite here? What new term do I add here? Instead of just mu naught J, I also have to add mu naught times what? Times epsilon naught times partial E partial T. Just like over there is partial B partial T. Okay, so you see, a changing magnetic field can cause an electric field, and a changing electric field can also cause a changing magnetic field. So now there are two ways to generate a magnetic field. One is by moving electric charge, the other is by changing the electric field. And there are also two ways to cause an electric field. One is by having electric charge, and the other is by having a magnetic field, variable magnetic field. Okay, so that completes the Maxwell's equations. We add this ever so important new term. Okay, so naturally the next question you may ask is, what's so good about this new term? What can we get when we add this new term?